In this video, we want to talk about linear approximations. Do you remember back in Calc 1, we did linear approximations? That is, we had a function, y equals f of x, and we said, hey, near the point x equals a, I want a linear function. That is something, graph is a straight line, that looks a lot like the function that I have. In fact, I want it to have the same function value at a, and I want this linear function to have the same slope that the function does at a. Right? So we came up with this function here that, if you plug in x equals a, then the a minus a is a 0, and this is 0, and you just get f of a. So L of a, it would equal f of a. Good. And also, since this is just a linear function, that is, it's just x to the first power, that we find the slope, well, you can do it by taking the derivative, or even before you knew calculus, you could find the slope of a line. It's the coefficient in front of the x, right? So the slope of this line is f prime of a, which is exactly the slope of the function at a, right? You take the derivative, you plug in a, that tells you the slope at that point. So this is a linear function, and it matches the function f at a, and it matches the slope of f at a. This is what we call the linear approximation. But it turns out this is, we have another name for it too. It's called the tangent line, right? So at the point a comma f of a, this line matched the function, right? It's the tangent line. Now, we want to do the same thing, but more variables, right? So now we've got function of 2 variables. So the surface is so the graph is a surface, and we're going to do a linear approximation. So f of xy is approximately equal to L of xy. And we want it to match the function at some point a, b. And we want it to match the partial derivatives at a, b. Right? So what I do here is L of xy is f of ab plus the partial of f with respect to x at ab times x minus a plus the partial of f with respect to y at ab times y minus b. Notice that if I plug in ab, that this turns into a 0, the b here turns that into a 0, and I just get f of ab. So sure enough, L of ab equals f of ab. Likewise, if I take the partial derivatives of this with respect to, let's say, x, this is a constant. All of this stuff is just y's, that's a constant. And so you just have this linear function here, something times x minus a, and the derivative is just the coefficient in front of the x. So what is the partial derivative with respect to x? Well, it's the partial of f with respect to x at ab. So partial of L is equal to the partial of f, right, at ab. Likewise, when you take the partial with respect to y, you're just going to get this thing, which is partial of f with respect to y at ab. So Ly equals fy at AB, right? Not anywhere else, but just at that point. So what we have here is the linear approximation, which, hey, if you watched the last video, you know that this is the equation of the tangent plane, right? And so using the tangent plane gives us an ability to approximate the function with a simpler function. So for instance here, here's an example. I've got f of x equals the square root of x squared plus y squared. This, if you look at the graph, is actually a cone. And I want to estimate what is f of 3.2 comma 4.1. And, if I had a calculator, I could just plug it in and find out. But that's not the point here. The point here is I want to approximate it with a linear approximation. Sometimes the functions are more complicated, or you don't find yourself with a calculator handy. And we can do these linear approximations. So notice at 3, 4, this is particularly easy to calculate because 3 squared is 9 and 4 squared is 16 and 9 plus 16 is 25 and the square root of 25 is 5. I don't even need a calculator to get that. The partial with respect to x of this function I'm thinking of this to the half power, so it's 1/2 this thing to the minus a half times the derivative of the inside, which I'm taking the partial with respect to x, so I just get a 2x. The 2 and the half canceled out, and there's my partial with respect to x. When I evaluate it at the point 3, 4, Plug the 3 in for x, the 3 and the 4 in for x and y, and I get 3/5. Likewise, take the partial with respect to y. It looks a lot the same, but when you take the derivative of the inside, it's derivative with respect to y this time. This is a constant, and you get a 2y out of it. The 2.5 cancel out, making this. And plug in a 3, 4, and I get 4/5. Okay. So my linear approximation is, I start with the function value at 3, 4. Then I have the partial with respect to x at 3, 4 times x minus 3. And then plus the partial with respect to y at 3, 4 times y minus 4. And there's my linear approximation. There's my tangent plane. Right. Now I can, instead of plugging 3.2, 4.1 into the function, I can just plug it into the linear approximation. And that's a little bit easier calculation to do. And I end up with 5.2. Now, I want to check just to see how close we were. So I can find the actual function value is actually 5.20096 and some change here. So you can see that that linear approximation was actually pretty good. And this is the point of the linear approximation, in that as long as you're close to the point where you calculated the linear approximation, then your function values are going to be pretty close to the actual thing. The further you move away, if I plug in 72, 42, that's probably not going to be very good, because by the time you move out that far away from 3, 4, the tangent plane isn't going to be close to the surface anymore. Now you might get lucky and the surface comes back to it or something, but in general it's not good. But stay close, and your outputs will be close. So there you go, linear approximations. A plane that matches the surface in function value and in first partial derivatives at a particular point, the linear approximation.